So before I discuss entanglement, do we have questions about this?
So what do their graph look like?
That's a very good question. Yeah. So here, let me show you the graph from the book. Okay, that way I'm not making. Here. Okay, so what we have here is in the x-axis, we have the argument, and this is for small values. And the y-axis is the Fermi-Dirac statistics, and okay. So here we have a logarithmic scale, and here we have a linear scale. The upper panel shows the distribution with linear vertical axis, and this one shows a logarithmic vertical axis. So for large values of the argument, the three distributions, they look the same, right? But for small values, the Bose-Einstein statistics, that kind of diverges, right? Whereas the Fermi-Dirac statistics, that gives you it converges. Okay. Now,
So could you please repeat where the Bose-Einstein and Fermi-Dirac equations are used? Are they both for quantum gases?
yeah, for quantum matter, if you like. I mean, for example, for Bose-Einstein, there's one of the application for Bose-Einstein statistics is the Bose-Einstein condensate. So, for example, what happens is at very low temperature, a lot of the, for example, in liquid, I think it's in liquid helium or systems like that. All the different particles, they occupy the same state and they behave like, and as a result, you get these exotic properties like superfluidity. Whereas for Fermi-Dirac statistics, you have applications in neutron stars. So neutron stars have something called the degeneracy pressure. Degeneracy pressure. So the idea is that, a neutron star is created when a supermassive, like a red giant or something, like a very massive supergiant star, it goes supernovae and it sheds all the matter except neutrons. So it's a very dense sort of, object. But then you might ask, well, there are, on a neutron stars, the nuclear processes that kept the star creating energy is no longer there. So what is keeping the neutron star from collapsing further under its own, gravitational pull, right? It turns out the thing that is keeping it together and not collapsing further is known as this thing called the degeneracy pressure. Now, what is the degeneracy pressure? It just means that if you have, because all the neutrons are fermions, because of the Pauli exclusion principle, you cannot pack them in the same place, because then you would be, putting them in the same state, right? And that creates a natural repulsive force between the neutrons, and that is known as degeneracy pressure. But there's a limit to this pressure. The degeneracy pressure, there's a limit, and that was computed by Chandrasekhar. So Chandrasekhar was a young Indian student who went to Cambridge to do his PhD, and he was on his way to Cambridge to do his PhD with Arthur Eddington, but he took a ship, and back in those days it took a long time, and to reach the UK. So he decided to keep himself occupied on the ship, and he derived the limit that the mass of the star has to satisfy for the degeneracy pressure to be enough to keep the star, from collapsing. And that limit is known as the Chandrasekhar limit. So above the Chandrasekhar limit, a star can become either a black hole or depending on whether it's a black hole or a neutron star. Okay, so that's an application of Fermi-Dirac statistics. Okay, so there are many applications. I mean, the applications in condensed matter physics. I'm not really a condensed matter physicist, so I don't know all the applications, but there are many applications.
Sir, the strange quark, is that a fermion?
Yes, all quarks are fermions.
So the strange matter, something is called the strange matters. The scientists say that they are very low state. So every matter wants to turn into a strange matter. Is that true?
Yeah, I've heard stuff like that. I haven't really looked into the theory of it, so I'm not exactly sure. But yeah, I've seen like videos on it. I perhaps I know as much about it as you do. So okay, let me just go back and see if I can do a little bit of entanglement. Is that all right?
Yes, sir.
So, we looked at tensor product states. So we looked at, and so suppose that we have a state. Now let's ignore spins and stuff like that. And suppose we have a state of two particles, and the first particle is in state 0. The second particle is in state 1, and and then we have something like this, right? Now, suppose that we create two particles which are in this state. Now, suppose that particle number 1 goes in this way, and particle number 2 goes in this way. So this is lab A, Alice's lab, and this is Bob's lab. And suppose that Alice and Bob are far away, and that they decide they have a pre-arranged agreement that at a specific time they're going to observe the particles. So suppose that Alice observes. Okay, suppose just Alice is going to observe particle, do an experiment on her particle. So Alice observes the state of the particle, and she finds that the particle is in state 0. Okay, particle 1 is in state 0. Then my question is, what is the state of Bob's particle then? Can someone tell me?
1.
Exactly. So essentially what happens is, by that observation, Alice collapses the wave function from psi to just the first factor. And therefore, Bob's particle must be in state 1. But if Alice were to find it in state 1, then Bob's particle would be in state 0, right? So now the thing is that, it seems like Alice's action is influencing what Bob is going to see, right? So, and it could be that Alice, so, when Bob looks at this particle, suppose Bob looks at that particle a millisecond after Alice does her experiment, and such that, their distance between them is such that a millisecond is way too short for light to propagate between Alice's lab and Bob's lab. So that means that as soon as Alice makes a measurement on her particle, the influence of her experiment propagates to Bob's particle faster than the speed of light. So this is something that made Einstein very suspicious of quantum mechanics. And he tried to create a paradox, which is now known as the EPR paradox. And what Einstein said, that maybe, there are hidden variables that is not accessible to quantum mechanics, and those hidden variables mean that somehow secretly, Bob's particle know which particle Alice's particle is going to choose, and therefore, that allow Bob's particle to choose the right particle. So these are known as hidden variables. So Einstein said that there could be some hidden variables. But it turned out that a gentleman called Bell showed that local hidden variables implied that a certain inequality be satisfied. There is some inequality known as Bell's inequality must be satisfied. And what is astounding is that quantum mechanics violates this inequality. So there's more correlation in quantum mechanics than there would be if there were local hidden variables. So this spooky action at a distance is something that happens in quantum mechanics. Now, the thing that is interesting is that although there is some sort of spooky action at a distance in quantum mechanics, you cannot use it to send information. So although there is something travels faster than the speed of light, it is not information. You cannot use it to send information. Okay, so this is very, very interesting. And so this phenomena is known as entanglement. And entanglement is used, has a lot of application. So for entanglement, has application in quantum computing. Or quantum information. So in quantum computing, entanglement is as a resource, and by doing something in one part of the quantum computer, you can do something in a different part of the quantum computer. And another application of entanglement is in teleportation. So you can use entanglement to teleport quantum information from one place to another. Okay, but still you cannot violate the speed of light, or you cannot send information faster than the speed of light. So for example, there's an analogy that people use. Suppose this is the Earth and there's the Moon, and you have a laser beam that is pointed to the north pole of the moon, and you flick the laser beam very quickly, then this beam goes to the south pole. So the tip of light travels across the surface of the moon faster than the speed of light, depending on how quickly you flick your laser on Earth. So the tip of light is traveling faster than the speed of light, but that doesn't mean there is any information traveling faster than the speed of light. So that's an analogy sometimes people use. Okay, I think I have enough. I don't have any more things to say for today. So I'm going to list the lectures that I want you to look at for next Tuesday's quiz. But before I move on and do the attendance, are there any questions? Oh, yeah, there are questions in back channel chat. Okay. Why does the Bose-Einstein graph diverge at lower energies? Okay, that's a very interesting, it's actually unphysical. So if in bosons, the probability that beta times E minus mu is negative is massive. Beta is roughly 1 over T. So if mu is small, then the probability of E is less than mu is massive when T is small. Right. I think these are those are very good questions. Let me come back to those in the next lecture, if you don't mind, because I think I have to think a bit carefully about that.
Sir, how to entangle two particle in a lab?
Right. One way of entangling two particles is to pair create them. So suppose that you have for example, a photon can can become a positron and an electron. So a photon, if you give it near a heavy enough object, can be turned into a positron and an electron. You need the object for momentum conservation, otherwise it doesn't happen. And then you can separate them, and then it turns out that the joint wave function of these two guys is in an entangled state. So look at the experiments of the Elaine aspect. So he has actually done experiments in that are related to the EPR paradox. Okay.
So did anyone solve the entanglement thing yet?
What do you mean solve?
Solve, I mean explain how does they how does it say,
I
just
see.
ধ্বংস হয়ে যায় একসাথে?
Why,
How does
how does it happen? No,
instantaneously?
I mean, this is it. I mean, the tensor product structure just implies this. This is part of quantum mechanics. There are different schools of thought. Some people say that, oh, there is hidden variables, but they're not local. So it turns out that if you say the hidden variables are non-local, then you can violate Bell's inequality. And there are non-local hidden variable quantum theories. That's one solution, but it's an ugly solution in my view. And there are problems with that approach too. And then there are people who say, oh, this has something to do with quantum gravity. And those crazy people are people like Leonard Susskind, who say that, oh, EPR is actually equal to ER. ER means the Einstein-Rosen bridge, which is basically the historical name for a wormhole. So some people think, people like Susskind, they think that when two particles are entangled, they are somehow related by some some um, they are related by some wormhole. So this is very highly speculative, as you can see.